Okay, in this video, we're going to go through the ground reaction forces and the vertical dimension for the counter movement jump. So what's counter movement jump? Make sure you watch the video that has this as an example. Pretty simple task. We start in a standing position. We squat downwards, so counter, and then we move upwards. We eventually take off from the ground. We're in the air, we're jumping, and then ultimately we're landing. So this region right here is flight. This region here is the jump phase. And then finally, we would have over in this region here, landing phase. Okay. I'm going to sketch out the ground reaction force for the jump phase. In another video, there's ground reaction force in landing. We're obviously not going to do ground reaction force during flight because you're not in contact with the ground, so the ground reaction force is 0 during flight. But I'm really interested in trying to understand the ground reaction forces during the jump portion of the movement where we go down and then up. All right, so let's pull out our model for PVA ground reaction force, okay, for the counter movement jump. Remember, up is positive, always. So let's look at this. We're going to start in a standing position. We're going to go downwards and immediately go upwards and then take off into the air. And I'm going to do a dotted line to represent flight. Okay, now I'm going to drop down my line here so I can see it on each of my plots. I'm going to call this discrete event takeoff. Takeoff. Sometimes we'll call it toe off, but it's takeoff. It's the beginning of the flight phase. And I'm not going to put landing in this plot. Okay, that comes later. Here's the start of the movement. I'm going to drop down that discrete event so it shows up on each plot. Okay, and this is the start. So this entire portion here is the jump phase, then the flight phase. We go down and then up, we take off into the air, and eventually we reach a high point. We can measure that, it's a jump performance, something like that. All right, so let's do our PVA, knowing our relationships between each of these parameters. Slope of the position versus time plot tells us everything we need to know about velocity. The slope of the position time plot is negative in this region. Velocities will all be negative. Negative velocity indicates downward movement. The slopes are all positive. All velocities would be positive in this phase. So sometimes we call this subphase downward and upward. Some references may say eccentric and concentric. That's it's okay, but I tend to call it downward and upward phases. And then we take off into the air. So all these velocities are negative, all these velocities are positive in each of those phases. Velocity initially is 0, the person's standing still. What's the velocity at takeoff? It's not 0. In fact, if I look at the slope in this region, it's going to be some positive slope. Depending on how high we're going to jump, that velocity at takeoff will tell us how high exactly we will jump. Because once we take off, what's happening is we're a projectile. And once we take off, we're no longer pushing on the ground. Velocity will slow down while moving upwards. The higher we make the velocity at takeoff, the longer we'll be in the air, and the longer velocity will be slowing down. So we end up jumping higher. So the velocity at takeoff is a positive number. I'm going to put a dot right there to represent that moment in time that velocity is, that the person's no longer in contact with the ground. After that, velocity slows down at a rate of negative 9.8 meters per second squared. That's the flight phase. A equals negative 9.8 meters per second squared. The slope of this line is negative 9.8 meters per second squared. And the way I've drawn this, I would actually identify the highest point of the jump is right where velocity passes through zero. Why is acceleration negative 9.8 meters per second squared? Because the person's in the air and the only force acting on the person is the force of gravity. And gravity causes all objects to accelerate negative 9.8 meters per second squared. All right, so I've got that part figured out. I've got this part figured out. I've got the directions of the velocity figured out. Now I need to just put in how the rate of change of position is changing through here. Well, initially, we're speeding up, moving downwards, then we're slowing down, moving downwards, then we're speeding up, moving upwards, right at the end. And notice I didn't say slowing down, moving upwards, but there is a little bit of slowing down, moving upwards, and I'm going to explain that as we go along. So my velocity plot is going to look like this. And notice what I'm going to do. I'm actually going to make the fastest velocity occur right before takeoff. The fastest velocity that we're going to see will be right before takeoff. All right, so now let me drop dotted lines down at the max and min because it's easier to see some things. And I'll drop this one down here too. This is all downward, down, and these are all up, and then even over here, this is all up. As long as the velocity is positive, direction of movement is upward. Once velocity goes negative, we're moving downwards. Speeding up, moving downwards, slowing down, moving downwards. Speeding up, moving upwards. Oh, shoot. I messed up. Forget about that. This phase right here, this phase is also up. Sorry, I messed up. Sorry, my writing is getting a little up. We're still moving upwards, but we're slowing down, moving upwards. This is all upward too. So this is just a special little phase in there. Okay, now let's go down to acceleration. Well, we know the slope of the velocity versus time plot. This is everything we need to know about acceleration. So acceleration will be negative in this region, positive in this region, positive in this region, negative in this region, and negative in this region. If you can pick up the positive, negative accelerations and where acceleration will be zero, you are doing great. So those are zero accelerations at those points. Oops, sorry, at this point. Oh, I need more coffee. All right, so now I'm going to draw out my acceleration plot. It's going to look like this. The dotted line being acceleration, negative 9.8 meters per second squared, because the force of gravity is the only force acting on the object. So now I have regions of positive acceleration, regions of negative acceleration. Now notice I did not make, and sorry, that was a mistake to put that there. I did not make this peak be any particular spot in here. And the peak acceleration can happen anywhere in this region. And sometimes we may even get two peaks. And that is usually when we start using the arms or we start doing some type of jump technique where we might get a double peak in here. And I'll show you some ground reaction forces later where we actually see that. So this peak does not have to occur in any specific region in here. Okay, it does not need to occur where that line is drawn there. But I do have accelerations that are positive, accelerations that are negative. Well, remembering our equation, FGRF equals MACOM plus FG. I can now draw my ground reaction force. Make sure you watch the other videos because I do faster and faster each time. Like a ground reaction force that looks like that. I'm going to draw a dotted line across just to represent body weight. And now you can see that in this region where acceleration is negative, ground reaction forces are less than body weight. Anywhere where acceleration is positive, ground reaction force is greater than body weight. Anywhere where acceleration is negative, ground reaction forces are less than body weight. But remember, this is all upward movement. Oh, wow, all downward movement. And this is all upward movement. Okay, even all the way over the way I've drawn it to about here, where velocity passes through zero. So now I've got a ground reaction force that looks like that, but I have in this mixture of ground reaction forces, I have some downward movement and some upward movement. I have some speeding up moving downward. I have some slowing down moving downwards. And then I have speeding up moving upwards. And then this last region is slowing down moving upwards. And the reason that this happens is right at the very end, right before takeoff, you just can't push on the ground hard enough with your toes trying to extend. And so even though you're still pushing on the ground, you just are not able to push that hard, and gravity ends up being greater than the magnitude of force that you can generate, and therefore greater than the ground reaction force that you can generate. And therefore you start to slow down when you're jumping upwards near the end of that jump phase, even though you're still in contact with the ground. So to jump higher, you want that period of time to be really small, and you want to slow down the least amount because you want that velocity at takeoff to be as high as possible. So everything that you're doing for creating forces in this region, you're trying to generate the fastest velocity at takeoff. Okay, so this is our counter movement jump. And you can see this region here where ground reaction forces are less than body weight, we're moving downwards. In this region here, forces are greater than body weight, but we are still moving downwards. Forces greater than body weight, moving upwards. Forces less than body weight, but still moving upwards. How do you interpret these data? You have to understand the kinematics and really understand the velocity plot. Okay, so I'll show you some ground reaction forces that we actually can collect of our counter movement jump. And you'll see this same pattern, and then we'll be able to interpret it. Okay, thank you.